You're welcome to today's class, and we are still going to continue from where we stopped. Okay, we're going to continue from where we stopped. We have been taking the 2010 JAM Chemistry past questions. Okay, we have done number 1, number 2, number 3. So we are going to move to number 4. We are moving to number 4. So, and in the number 4, the question is, the droplet of water observed around a bottle of milk taken out of the refrigerator is due to the fact that A, the water vapor in the air around the bottle gains some energy from the bottle. B, temperature of the milk drops as it loses heat into the surrounding. C, saturated vapor pressure of the milk is equal to the atmospheric pressure. D, water vapor in the air around the bottle loses some of its energy to the bottle. Wonderful question, technical question. And that's the reason why we need to understand, some of those topics before we are able to answer the question. I said earlier in my previous classes that for you to answer correctly these questions, the first thing you need to do is to actually know where they brought the question from. So where did they bring this question from? Where did they bring this very particular question from? They brought this question from kinetic theory of matter. Yes, that's where they brought this very particular question from. They brought it from kinetic theory. They brought it from kinetic theory of matter. And we are going to explain that, we explain that explicitly in today's class, so that any question on kinetic theory of matter, we are going to answer them correctly. So the first thing, kinetic theory of matter, we have 3 keywords here: kinetic, theory, and matter. So let's start from the word kinetic. Of course, when you talk about kinetic, you are talking about movement. That's the meaning. When you talk about kinetic, you are talking about movement. Very important, which means if you are talking about kinetic, we are referring to something having the ability to move. Very, very important. When you talk about theory, if you talk about theory, you are talking about what is generally accepted. Okay? When something becomes a theory or a law, we say it is generally accepted because accepted. Okay? It's generally accepted because it has gone through all the scientific stages, and now we can say this thing is what is scientifically correct. And from matter, which is the basics of chemistry itself, says anything that has mass and occupies space, anything that has mass, that's our normal definition, thing that has mass and occupies space. Okay? So now, bringing these keywords together, we have that kinetic theory of matter, which means our normal state of matter, which are solid, liquid, and gas. They are telling us that there is a kind of movement they exhibit, and that's why we are saying it is now a theory. Okay, the reason why it is a theory is because some of these theory postulated by these scientists are generally accepted because this very particular state of matter actually has this very particular property. So when you talk about kinetic theory of matter, you are talking about the ability of your state of matter, either your solid, liquid, or your gas, to actually move. Okay. Now, very important, we know that our matter, is divided into 3, as we know. We say it as divided into solid, into liquid, and into gas. I hope this is very clear. So our matter, which is the solid, which is liquid, which is gas, they actually will regard them as matter because these are the states of matter. Now, the meaning of this topic is that if we have kinetic theory of matter, it means our solid or our liquid or our gas can be in a kind of movement which we want to talk about, extensively in today's class. Very, very important. Now, let's talk about our solid. Let's talk about solid. I'm talking about our matter existing in these three states, which is the solid, which is the liquid, and which is gas. So what are the properties of solid? If something is solid, what are the properties of solid? Very important. What are the properties of solid? We say one, their molecules. The molecules of solid, their molecules are closely packed. The molecules of solid are closely packed. I want to believe we are together. The molecules of solid are closely packed. The molecules of solid are closely packed, which means that if I have a, let's say I have a container, and these are the molecules of solid, you see them, they are jam-packed, they are closely packed. Okay? You can see them. The molecules of solid, they are closely packed. Very important. They are closely packed. Now, and because of how their molecules look like, they don't have that, free movement. They don't have that free movement. They don't have that free movement. They don't have free movement. Of course, you don't expect them to have free movement because their molecules is already closely packed. Is closely packed. So because their molecules are closely packed, they are held firmly. Yes, they are held firmly. They are held firmly. They are held firmly together by force of cohesion, held firmly by force of cohesion, and that's the reason why they don't actually move. I'm still talking about the properties of solid. They are held together by force of cohesion. Our basic chemistry, our elementary chemistry, your force of cohesion could be electrovalent bonds, could be electrovalent. Our force of cohesion could be electrovalent, okay, could be covalent, could be our van der Waals force. Yes, could be our van der Waals force. So could be our van der Waals force. So they are held, by force of cohesion, and the force of cohesion may be electrovalent bond, may be covalent bond. In fact, may even be metallic bond. These are likely bonds that can hold the molecules of solids together. Okay, so we can have electrovalent bond, we can have covalent, we can have van der Waals force, we can have even the metallic bonds holding the molecules of solid. I want to believe we are. Are we still together? Are we still together?
Yes, sir.
Are you still seeing my screen? You guys are seeing my screen, right?
Yes.
So can we continue? Okay. So it could be our electrovalent bond, it could be covalent, it could be van der Waals force, it could be metallic bond. So this bond tends to restrict their movement, and that's the reason why you see this shape I drew, this very particular diagram I drew. Okay, this very particular diagram I drew, you see the molecules of solids, they are closely packed, and the reason why they are closely packed is because they are held firmly by force of cohesion, and the force of cohesion could be our electrovalent, covalent, van der Waals force, or our metallic bond. So this very particular bonds bind their crystal structure together. These very particular bonds bind their crystal structure together. Yes, bind their crystal structure together. And as a result of this, because of this cohesive force binding it together, it restricts their movement. Yes, their movement is restricted. Very, very important. And that's the reason why they will be held in fixed position. Your molecules of solid are held in fixed, okay, they are held in fixed position because of the kind of bonds that is holding them together. And as a result of this, your solids, please take note, your solids can only, okay, can only vibrate, can translate, can rotate, can vibrate, can rotate, but cannot translate. I will explain that. But cannot
Sir, I have a
translate.
question.
Okay, I'm coming. I'll answer your question. I'll answer the question. Just let me explain this, then I'll take your question. So our solids can only vibrate, okay? They can rotate, and their vibration or their rotation happened, at their fixed positions. Don't forget that we said there are bonds that are binding them together, which is either the electrovalent, which is either the covalent, the van der Waals force, or the metallic bond. So as a result of these forces binding them together, what happens is the molecules of your solids, they can only vibrate, okay, they can rotate, but they cannot translate. The meaning of translating here means they cannot move, which is what you have said, because of the bond that is actually binding them together. Very, very important. So your solids can only vibrate, okay, can only rotate, but they cannot translate. And their vibration and their rotation will be happening at their fixed position, but they cannot move from one place to another because of the bond that you have there. But now I'm going to take your question. Let me just explain this, then I'll take your question. Is the question on this very particular solid I'm explaining? Hello, can you hear me? Hello?
Yes, sir.
Okay, is the question on the solids I'm explaining?
Yes, sir.
Okay, you can ask your question before I continue there, so you don't forget. Okay, ask your question. I can hear you. I can hear you. I can hear you. Ask your question. Hello, I can hear you. Ask your question.
Sir, among those forces, which one of them has the weakest force of attraction?
Okay, among the electrovalent bond, the covalent bond, the van der Waals force, and the metallic bond, right? Are you still with me? If I get your question right, you said the electrovalent bond, the covalent bond, the van der Waals force, and the metallic bond. The which one has the weakest, or which one is the weakest? Of course, that's the reason why, our elementary chemistry made us understand that your van der Waals is not really a bond. That's why if you look at the name here, it's a force. That's the reason why our bonds are divided into two. We can have intramolecular force. Our forces are divided into two. We can have intramolecular force and intermolecular force. So your intramolecular forces are forces in between atoms, and that's where you have your electrovalent bond, you have your covalent bond, you have your metallic bond. Those ones are intra. But your van der Waals force, like hydrogen bond, van der Waals force, all those ones are our metallic bond, our hydrogen bond, van der Waals force, they are inter. So out of all these bonds now, the weakest is the van der Waals force. Yes, that's the reason why we are not really referring it as a bond. It's not really a bond, it's a force. I think maybe in subsequent classes I'll still come to explain, Van der Waals force. Still come to explain Van der Waals force. So the weakest out of all these bonds I mentioned here is the Van der Waals force. Are we still together? Have I answered your question? Are we together? Have I answered your question? I can't hear you. Can you guys hear me?
Yes, sir.
Okay, so I should continue. Is that question? Have I answered your question? Somebody asked that question. Have I answered the question?
Yes, sir.
Okay, so let's continue. Let's continue then. So very, very important now. Our molecules of solids, they can only vibrate, they can rotate, but they cannot translate. That's an important factor we need to note. Another property of solid we need to know is that it has a definite shape. They have definite shape, okay? Yeah, they have definite shape and they have definite volumes. They have definite shape and volume. Of course, what are examples of that? That's the reason why if you see a shape, you know when it is a cube. If you see a shape, you know when it is a cuboid. All these things are solid shapes. Okay, you know when it is a sphere and the rest like that. So the reason is because they are solids. Okay, and that's why even in mathematics, they will always refer to them as solid shapes. Okay, that's the reason why we said they have a definite shape, because cube is actually different from a cuboid. A cuboid is actually different from a sphere. A sphere is different from a cylinder, and like that. So very, very important. They have definite shape and they have definite volume. Yes, that's the reason why even in the world of mathematics, you can always calculate the volume of those solid shapes because they have depth. You can actually put something inside. They can contain something. That's the reason why we say they have definite what? They have definite volume. So very, very important. Understand that aside your solids able to vibrate and rotate and cannot translate, they have definite shape and they have definite volume. And another one I want us to understand is what? They are difficult. They are difficult to compress. So they are difficult to compress. What's the meaning of them being difficult to compress? It means that you cannot force them to occupy a place. Yes, it's just like you taking a very big stone, and you want to put it in a bottle water that has a very small amount. For you to be able to do that, it will be very difficult. Why? Because that very particular stone cannot contain that very particular cylinder or water bottle, and there is no way you can make it smaller for it to enter that very particular place. And that's the meaning of it being difficult to compress. So our solid is what is difficult to compress. Very, very important. Now I want us to understand something here. I want us to pay attention here because I want to be explaining something now for our solids. For our solids, please listen to it. When our solid is heated, you will agree with me that your heat is a form of energy. Heat is a form of energy. Heat is actually a form of energy. And when we talk about energy, we are talking about ability to do work. Okay, so when you eat a solid, what happens? When you eat solid, you have provided the molecules of the solid, you have provided them with what? With a lot of energy. So what will happen? What will be the effect of the energy? The effect of the energy will now be that it will increase the vibrational motion, it will increase the rotational motion, which means that if they are vibrating, let's say for example, they are vibrating with let's say 20 joules of energy. What happened? You have heated it, and when you heat it, you have provided them with extra energy. So what happens? These 20 joules of energy will increase to like 40 or 50 or 30, depending on the amount of energy that is that they are being heated to. So what happens? Their vibrational and rotational motion will increase. Their vibrational motion It will have effect on the vibrational motion, and it will have effect on the rotational motion. When you apply it to the molecules of solid, it will have effect on the vibrational motion, and it will have effect on the rotational motion. Don't forget that there is a force that is binding them together. Okay, don't forget that there is force that is binding them together. So as at that very particular increment in vibrational motion and rotational motion, what happens? The vibrational motion or the rotational motion will now increase. So it will get to a point as you increase and increase the energy, it will get to a point where the vibrational and rotational motion will overcome the binding force. We overcome the binding force. And why is this like this? The reason why the vibrational motion is now overcoming the binding energy is because you are applying its energy, okay, to the molecules of the solid. So what happens as it begins to vibrate vigorously, because you are adding energy to that very particular substance, as it begins to increase and the vibrational motion begin to what? Vibrate vigorously, it will get to a time where the vibrational motion will now overcome the binding force. So when the vibrational motion overcomes the binding force, what happens is the melting of the solid. So what happens will now be the melting of the solid. So in other words, I can define melting point of a solid to be the point at which my vibrational motion will increase and overcome binding force. I want to believe we are still together. So when our vibrational motion increases and it overcomes our binding force, what happens is that the melting of the solid takes place. And at this point, where the vibrational motion, overcomes the binding force, at this point, you will agree with me that the particles will no longer be held in fixed position again. The particles will no longer be held in fixed position again. The question is why? Why will the particle not be held in fixed position again? Very simple. The vibrational motion has overcome the binding force. So the crystal structure has collapsed. That force that is holding them together has actually collapsed. So what happens? It is the melting of the solid that takes place. Please note this. Very, very important. So I can say my melting point of the solid is the point whereby vibrational motion overcomes binding force. Very, very important. Now, another thing we should note about solid is that if there is presence of impurity, in a solid, what is the effect? The effect is that it will lower the melting point of the solid. The melting point of the solid. It will lower the melting point of the solid, and it will cause it to liquefy gradually instead of suddenly. So instead of it to actually melt suddenly because of the presence of impurity, it will liquefy gradually. And that's why cases like iodine, yes, cases like iodine, though for iodine, what happens to iodine is iodine sublime. So in some cases too, it can actually, it can change directly into gas, which is our sublimation. You should know that our sublimation is where your solid turns directly to gas without undergoing the liquid form. So very, very important in some cases like iodine, the molecules will just break away from their crystals and change directly into vapor. So that very particular process is what we call sublimation. So very, very important, we need to understand the presence of impurity to melting point. What happens to what? Impurity is that when there is an impurity in a substance, it lowers the melting point of that solid, and it will allow it to liquefy gradually instead of it to actually, liquefy suddenly. But for iodine, of course, sublimation can occur in likes of iodine where they change directly from solid into what? Into vapor. So very, very important. These are what we should understand when it comes to what? When it comes to the molecules of solid. Very, very important. When it comes to the molecules of solid, what we need to understand is what we have highlighted so far. I want to believe we are still together. I want to believe we are together. So, having known about solid, let's move to the liquid state. We are still talking about the state of matter, the liquid state. The liquid state. So the liquid state now, very, very important. One of the state of matter is the liquid state. And the first thing we must understand about liquid state is that their molecules is not as closely packed as that of solid. We can be having something like this. We can be having something like this. Okay. Just trying to say that there is still spaces in between. There are spaces for liquid. So we can conclude that their molecules, the molecules of liquid are not as closely packed, like that of solid. So which means that they are still having spaces in between them, and because of that they will definitely vibrate. Okay, they can vibrate. That's molecules of liquid. They can vibrate, they can rotate and translate. And why can they translate? Translation is talking about their degree of movement. And why did we conclude that they can actually why did we conclude that they can actually vibrate and rotate? The reason is because they can reason is because they have spaces in between them coming. Can you guys still hear me?
Yes, sir.
Okay, I want to be sure you are hearing me. That's why I want to be sure you are hearing me. So very, very important. They can vibrate, they can rotate, and they can translate. And what is the reason? The reason is because they are having more spaces in between them. Okay, so don't forget that they are still under the influence of cohesive force, and their movement are restricted because the spaces between them is not that much. Okay, so their degree, though they can translate, but their degree of movement happening to my pen. Okay, their degree of movement, their degree of movement is still restricted, but not that it is restricted like that of solid, because solid they don't even have spaces in between them. But because there are spaces between molecules of liquid, their degree of movement is actually restricted. Okay, they can actually move, but the movement is not that free because there are still cohesive forces between them. So we need to understand that, and from there we still need to understand that because of this, a liquid will now has a fixed volume, a fixed volume but no definite shape, a fixed volume but no definite shape. Yes, they are fixed volume but they don't have definite shape. They take the shape of their container. Yeah, so if you put water, likes of water in a gallon, it takes the shape of the gallon. You put it in, a cup, it takes the shape of a cup. So they don't have definite shape, but they have fixed volume. And again, our liquid is hard to compress. Liquid is hard to compress. It's hard to compress too, and I've explained the meaning of the compressibility. It means that you cannot actually force the molecules of liquid to occupy a place. Very, very important. So we need to know that about our liquid. Now I want us to note something in liquid. What is the presence? We talked about the effect of heat, on effect of heat effect of heat on liquid substances. What is the effect of heat on liquid substances? Now, the first thing I want us to understand about liquid substances is that their particles are attracted by their are attracted by their neighboring particles in all directions, and that explains the reason why we have what we call, in your elementary physics, the reason why we have surface tension. Very important, because the particles are attracted by neighboring particles in all directions. That's the reason why we can have what we call surface tension, which is, water behaving like an elastic skin. We should understand that. Very, very important. Now, in a sample of a given substance, when you eat the molecules of liquid, what happens? Some particles will be energetic than others, because the one that is beneath that very particular beaker, or what you are using for eating them, will be more hotter. And when they becomes energetic, what happens to them? They break away from the attractive forces. They will break away from the attractive forces, and the liquid will tend to escape into the spaces above. Okay, and that talks about, all these things are interwoven, and that's why we need to understand them. And that's what talks about, your heat transfer by convention. So what happens? The molecules that are very hot, when they acquire more more energy, what happens? More heat energy, what happens? They replace the one up will replace them. So as they begin to gain more kinetic energy, or as they begin to heat them and they possess more kinetic energy, they can break away. Yes, they break away into the space above. And when they break away into the space above, we say they are vaporized. So the meaning of vaporization is now your liquid, turning into gas. So which means that if your liquid, acquire more kinetic energy as a result of them increasing their heat energy, what happens? They break away. And when they break away, we say vaporization has occurred. And that talks about, we can use what we do at home as example. You are boiling water and you left it for hours. If you leave it for hours and you get there in few hours after you have actually left it, you will not find anything in the kettle. Where did the molecules of liquid, where did they go to? They have turned into gas. They've turned into vapor. Why? Because they have acquired more kinetic energy as a result of the heat energy that is being applied on them, and as a result, they are break away into the space above and they turn into gas directly. Very, very important. So we need to understand that since evaporation is the escape, I talked about the escape of energetic particles. Let me write that so that we understand. So since our evaporation, you know is, we call it, is the escape. Let me use that word. Is the escape of energetic particles. How did they acquire energy? Because of the heat energy that is being applied. So the escape of energetic particles from the liquid, from the body, okay, from the body of the liquid, from the body of the liquid, very, very important. From the body of the liquid, they have say that they have actually vaporized, or they have evaporated. And we need to understand that your evaporation will occur at all temperature. Evaporation, you need to understand that evaporation, okay, evaporation occurs at all temperatures. At all temperatures. Yes, evaporation occurs at all temperature, and it's a direct proportionality, which means that when temperature increases, so as you begin to add it energy and the temperature increases, your evaporation rate too increases. So have it at the, in your mind, that have it in your mind that what happens to the water vapor in the atmosphere? How did they get there? And that's what this thing is explaining. The water vapor in the atmosphere, how did they get there? They got there by breaking away from their neighboring liquid. Why did they break away? Because we applied it energy on them, okay, or they gained it energy, and as a result, their kinetic energy increases, and as their kinetic energy increases, they broke away, and that's the reason why they turned into vapor. Very, very important. We should understand that. Very, very important. Now, another thing I want us to note here now is, I talked about your evaporation, which is the escape of energetic particles from the body of the liquid. Now, when the liquid is heated and the rate of evaporation increases, there is something we call saturated vapor pressure. Before I go to that, let me explain vapor pressure first. Let me explain vapor pressure. Let me explain vapor pressure. Let me explain vapor pressure. Now, what do you mean by vapor pressure? When when you heat a liquid in a closed container, when a liquid is heated in a closed container. What do I mean by closed container? When we say closed container, it means that nothing goes out, nothing comes in. Nothing goes out, okay, and nothing comes in. And that's what we refer to as a closed vessel or a closed container. Nothing goes out and nothing comes in. Now, when molecules are being heated, what do you think will happen when they break away into their neighboring liquids? They will not be allowed to go out, because we are actually eating it in a closed container. I want to believe you understand that now. We are actually, let me do this so that you understand. Let me say this is the container, okay, and this container has a lid. Okay, these are the molecules of the liquid. Do you understand that? So what happens as we begin to apply heat on this container? This very particular liquid here, we gain more kinetic energy and they want to break away, but they will not be able to break away. They will stay on top of this lid because this is a closed container. They cannot go out. They will stay on top of the vapor. We come here on this lid. We come here like this. We coming to stay on the lid. Now, what happens as you have more vapors on this lid? They begin to collide with each other. Yes, because a time will come where the vapors here will be too much and they don't have choice than they actually collide frequently with one another. So they'll be colliding with one another, colliding with the wall of the container, colliding with one another, colliding with the wall of the container. When this happens, we said they are going to exert a pressure. They will exert, they will exert a pressure. And the pressure they exert is what we call vapor pressure. Because who are those people exerting the pressure? It is the vapor here. And the reason why that pressure can be exerted is because it is performed in a closed container. Of course, you should agree with me that if it is in an open container, they will just break away into the space above and they turn into water vapor directly like that. Okay, so what happens is that as they begin to exert a pressure, a vapor, we call it a vapor pressure. So a vapor pressure is actually established. So don't forget that they cannot actually leave the liquid. So what happens if we now remove this heat that we have, we are heating this container before. If we now remove this heat that we are having here, what will happen to this vapor is that what they will re-enter the liquid, because as at that point they are going to what? They are going to condense. They condense. So what happens? They will re-enter. They re-enter the liquids. Okay. They will re-enter the liquid. So very, very important. When they re-enter the liquid, we say they have what? Condensed. So our condensation will increase as the vapor pressure. Our condensation will increase as the vapor pressure rises. I hope that's clear. So our condensation will increase as vapor pressure rises, because the more the vapor pressure, the more what we condense back to re-enter the liquid as our normal liquid. So when this happens, and as it happens like that, more and more liquid particles will evaporate. Thus, we now have two opposing forces are reoccurring in the system. Don't forget, it's just like you have a reversible reaction because it is in a closed system. So when it is a closed system, when A turns to B, B can actually turn to A. So we can have something like this. What will now be happening is our liquid particles, okay, our liquid particles, when they evaporate, we have our vapor particles. And when the vapor particles, when they condense, when the vapor particle condense, we have our what? We have our liquid particles. Very, very important. Now, but a time will come where the vapor pressure, when you are applying the heat, very, very important now. When you are applying the heat, when the heat is being applied, and the rate of evaporation will increase, because we have said as temperature increases, your evaporation too increases. A time will be reached when the saturated, don't forget those are the pressure that have contact with the liquid. The saturated vapor pressure will equal atmospheric pressure. Atmospheric pressure. So a point where your saturated vapor pressure, equals atmospheric pressure, what takes place is the boiling of the liquid. It attains boiling point of the liquid. And that's the reason why the boiling of liquid in all altitudes are not the same. Yes, if you boil water in higher altitudes, it's not going to boil at 100 degrees Celsius. I know you know that. Yes, because the vapor pressure there is not the same with the vapor pressure at the normal sea level. If you go to above sea level, which are high altitudes, normal sea level and below sea level, the temperature of water will never be the same. The reason is because the boiling point rather of water will not be the same. The reason is because as at that point the saturated vapor pressure is different. The saturated vapor pressure of liquid is lower in high altitudes, so which means that this very particular process where saturated vapor pressure equals atmospheric pressure will be faster. So the boiling point of water in high altitude will reduce. It will not get to 100 degrees Celsius. Don't be surprised. Yes, we need to understand that it will not get to 100 degrees Celsius before the water will boil at higher altitude, because the vapor pressure there is lower. So and when the vapor pressure is lower, it means that the boiling point is going to reduce. So we must understand that boiling point will be attained when the vapor pressure equals atmospheric pressure. Very, very important. And another thing we need to know is that the presence of impurities, the presence of impurities will increase the boiling point. Presence of impurity increase the boiling point of liquid. Yes, increase the boiling point. The boiling point of liquid. Increase the boiling point of to increase the boiling point of liquid, because what happen is that it will increase the time, or it will increase the rate at which your saturated vapor pressure will equal atmospheric pressure, and by then what will happen is that it will actually increase the boiling point. Unlike impurities that lower melting point of solid, presence of impurity will increase the boiling point of liquid. Very, very important. We need to understand that now. So note that our eating process now, from what I have explained, it means that eating will actually cause melting. When you eat the particles of solid, they melt. Okay, when you eat the particles of liquid, they boil. So eating will cause about melting, eating will cause about boiling, but cooling will cause, when you cool it, what it causes condensation, and it causes freezing. Please take note. And that's the reason why you see the boiling point of water is 100 degrees Celsius. The freezing point of water is around 0 degrees Celsius, and the normal temperature of water is around 27 degrees Celsius or thereabout. So look at this now. The normal boiling point of water is 27 degrees Celsius. What happens here? On going to 100, it means the temperature has been increased, which means we have heated it, and that's the reason why it's attaining the 100 degrees Celsius, meaning it is boiling. I don't know if you get that. While for our melting too, we need to heat the solids to gain more energy, and when they gain more energy, the binding force collapses and they melt. So but if we are cooling, look at this now. This is 0 degrees Celsius, so which means 27 degrees Celsius to 100 degrees Celsius, it means it is reducing. So it's just like you are cooling something, you are reducing the temperature. So when you cool, what happens is that your condensation and your freezing takes place. So I want you to take note of this, please. I want you to take note of this, which means that your condensation, okay, your condensation, which means that your condensation, is a process, whereby a vapor, whereby loses a vapor loses some of its kinetic energy. Please pay attention to this. Loses some of its kinetic energy to a colder body. And changes into liquid state. Please pay attention to this, please. to say here, don't forget that the reason why a liquid turns to vapor, okay, the reason why liquid turns to vapor is because we have what? We heated the molecules of the liquid and they turn to vapor. And the reason why they turn to vapor is because they have possessed more kinetic energy. You get that? When we heat the molecules of liquid, they possess more kinetic energy. And what happens is they break away, they become vapor, which means this vapor now, the reason why this vapor is because it has kinetic, it has more, possess more kinetic energy. Okay, now for this vapor now to turn back to liquid, what do you think will happen? The reason why this liquid turns to vapor is because it possesses more kinetic energy, okay, and that's the reason why it turns to vapor. I hope this is clear. So how will this vapor condenses back to this liquid, or how will this vapor turn back to liquid? You need to lose this kinetic energy for it to come back to this stage. I hope this is very clear. Liquid is going to turn to vapor by acquiring kinetic energy. They acquire more kinetic energy, so they break away and they turn into vapor. I hope that is clear. So for this vapor now to actually come back to this liquid, okay, for this vapor to actually come back to this liquid, what happens is that they need to lose this kinetic energy to become liquid. And that's what happens. You know, when you bring a carbonated drink, maybe your Pepsi, a carbonated drink, okay, you brought a carbonated drink out of the refrigerator. After some minutes, you'll be seeing droplets of water around that very particular carbonated drink. Droplets of water. What's the meaning? The meaning is that, you know, your carbonated drink is, is very, very cold, meaning the temperature here has reduces. The temperature here reduces. And around the carbonated drink, when you brought the carbonated drink out of the refrigerator, around that carbonated drink, okay, there are water vapor in the atmosphere, which is indicating an increase in temperature. So your carbonated drink is feeling that there is water vapor in the atmosphere, okay, water vapor in the atmosphere that has more temperature, and that's the reason why they broke away. They turned to vapor by possessing kinetic energy because of an increase in temperature. So what happened? Because your carbonated drink, the temperature is lower and the temperature of the water vapor in the atmosphere is higher, you will now see droplets of water around this carbonated drink. The meaning is that the water vapor around this carbonated drink is losing the kinetic energy they possessed before. It's losing the kinetic energy they have acquired before to turn into what? The droplets of water that you are seeing, which is a good example of condensation. I want to believe this is clear. So our condensation is a process whereby a vapor loses. So the vapor around that carbonated drink will lose kinetic energy. Why will they lose kinetic energy? Because their temperature is higher, and the temperature of the carbonated drink is what? Is lower. So they give back the kinetic energy they have possessed, and what happens is that it turns to it turns to it turns to liquid, which is water. So which means that when this very particular kinetic energy is being turned into droplet of water because of the kinetic energy that you have there, droplet of water, and you begin to cool the liquid. Don't forget, you cooling the liquid means it is losing heat to the surrounding. Very, very important. Water is 27 degrees Celsius. Normal temperature of water is 27 degrees Celsius. And we say that, it freezes at 0 degrees Celsius. 27 to 0, what happens? 27 to 0 means the temperature is reducing. So when the temperature begins to reduce, what happens is that it will attain a point which we call the freezing point. It will attain a point which we call the freezing point of liquid. So you attain a point where we call the freezing point. Attain a point where we call the freezing point of liquids. So very, very important. So When a liquid cools, it will lose its energy to the surrounding, very, very important, and the temperature will what? Will drop. So when the temperature drop and it drops and keeps dropping, what happens is we attain the freezing point. Yes, and we call it the freezing point of what? Of liquid. Very, very important. Are we still together? Let me know if we are still together. Are we still together?
Yes.
Is the explanation clear? I can't hear
Yes.
you. Is it clear?
Yes, sir.
Okay, awesome. Let's continue then. Let's continue. If the explanation is clear, so let's continue. So very, very important, it gets to a point where we call the freezing point of liquids. So take note of that. Very, very important. Now let's move to gases. I think that will be the one I'll conclude. Let's talk about gases now. Let's talk about gases. Oh, so gases show, different properties than that of liquids, and we need to understand that it shows different property because if you have a container, you know, gases are they have space in between them. They have space in between them. So because of the space in between them, what happens is that they have more kinetic energy. They have more kinetic energy. Because of the space in between them, they have more kinetic energy than even the solid and the liquid. And but there are still some school of thought will say there are coercive force in gas, but we come to say that their coercive force are negligible, and I'll explain why. Their coercive force are negligible. And why do we say their coercive force are negligible? We are saying that there is force in between something and they are still widely separated. So which means the coercive force is insignificant. Of course, we agree that the forces are there, but they are insignificant. Because what we know force for is to actually hold two things together, to bind them together. But here, the forces is not really binding this thing together. Okay, so we said their coercive force are actually negligible because they are free to move about in all direction, colliding with themselves and with the wall of the container. Very, very important. Colliding with themselves and with the wall of the container. So another characteristics of gas we should know is that they have indefinite shape and volume. Yes, they have indefinite shape. They have indefinite shape and volume. They don't have definite shape. They don't have definite volume. They have indefinite shape and indefinite volume, and they have high compressibility. They have high, okay. They have high compressibility. So you can force them to occupy a place. You can force them to occupy a place. You can force them to occupy a place. So they have high compressibility. So you can force them to occupy a place. A good example is your carbonated drink. When you open your Pepsi, your Coca-Cola, your Fanta, there is a gas that is evolved. And we call the gas the CO2 gas that gives it is a reacting taste. How did the CO2 gas get there? The reason is because they forced the gas to occupy that very particular place. And that's the reason why, at the slightest opening of those drinks, the gas want to run out because they're not comfortable. They force them. If they did not force them there, they should not try to escape. Okay, so it is because they have forced them there. That's the reason why they are looking for a way to actually escape. So that is that for gas is very, very important. Now we have some theories that are supporting the kinetic theory. We call them, the theories that support kinetic movement. or let's say phenomenal. That's how we say the phe, phenomena, phenomena supporting the phenomena supporting kinetic theory. So there are some phenomena supporting kinetic theory. We have the Brownian motion or movement. We have the Brownian movement. And you know that experiment is carried out by a botanist. Yes, the name of the man is Brown, and it's a botanist. What he just did is he tried to examine polygrain suspended. That's what the theory is, or the practical is like. You know, he examine polygrains suspended in drop of water. So when he looked at that using a microscope, and he saw that the polygrain was actually moving in the water. And he concluded that since this water is undisturbed, but in the microscope, he saw the polygrains moving in the water. He now concluded that yes, your molecules of water, they are actually moving. And that's the reason why we said the molecules of water are not that closely packed. Okay, they are not as closely packed as that of solid. So that was the theory to actually, establish the fact that the molecules of liquid are actually moved. Though their movement is restricted, but they still what move. And that's why they call it the Brownian motion, naming it after that very particular scientist. We have another one, we call it diffusion, and that's the movement of solid particles through a medium from higher to lower region. Movement of solid particles, solid particles from higher concentration higher concentration to lower concentration until their concentration until they are evenly distributed. Yes, until they are evenly distributed. Okay, we can see that in, when you use a perfume. For some of us that are, we are very, very used to using perfume. We're used to using perfume. So when you use a perfume, when you spray it, you that you are spraying it, you feel the concentration of that perfume, and before you know it, all your room begins to, all the spaces in the room, the perfume diffuse into all those places, and before it will now be evenly distributed. So very, very important. That's what diffusion talks about. And diffusion in gases is faster than you have it in liquid. Then we have, so the rate of diffusion in gases, let me do it like this. Rate of diffusion in gases is the fastest. In liquids is faster. In solids is fast. Let me use it that way. And you know the reason why it is like that. There are no spaces between solids. So since diffusion talks about movement, and there are no spaces between solids, so the probability that the movement will be faster is very, very low. So very, very important. But since gases, you have a lot of spaces in between them. So diffusion there is the fastest, while followed by liquid, and followed by solid. So solid has the the diffusion rate that is very small. Are we still together? Are we still together?
Yes, sir.
Okay. So another special type of osmosis, special type of diffusion rather, is what I refer to as osmosis. osmosis. Okay, and it's a special case of diffusion. Osmosis is still diffusion, but it's a special case of diffusion because what is involved here is a semi-permeable membrane. A semi-permeable membrane. Okay, and that's the reason why if you check your bean seed, for some of us that cook beans at home, after washing it and you put it in water, if you leave it for days, what do you think will happen? It will swell. It will swell. Why? There's movement of water molecules into the being seed through a semi-permeable membrane. So your osmosis too is still talking about diffusion, is a special case of diffusion. But what involves there is what is a semi-permeable membrane. Very, very important. You should know that. So conclusively, let me quickly conclude the class. And that's the reason why scientists, even in some textbooks, you will see this topic, they will not say it's kinetic theory of matter. They will say it is the kinetic theory of gas. And the reason is because, from the properties, you will see that gases, show different properties from solids and liquid. They don't have definite shape, they don't have definite volume, they have high compressibility. So unlike solid and liquid that is still showing some similar, they are still showing some similar property, but for your gases, they are different from solid and liquid. That's why scientists now say, okay, let us take time to actually talk about their gases because of their different characteristics from solid and liquid. So, and very, very important, gases, all these gases were now investigated by scientists like Boyce, like scientists like Charles, you know, Dalton, Dalton. All these are people that actually talked about all these guys, Gelusas and all the rest like that. So Gelusas and many more scientists like that. They are the ones that they studied about all these gases and came up with an assumption or with a theory. So we call it the kinetic theory of gas. We call it the kinetic theory. We call it the kinetic theory. Call it the kinetic theory of gas. So all these scientists worked on gas, researched on it and came up with some kinetic theory. And the first theory is the gas molecules, the gas molecules, gas molecules, they move in straight line motion, a straight line, colliding with themselves, colliding with themselves and with the wall of the container, collide, colliding, are colliding with themselves and with the wall of the container. Very, very important. And their collision are the collision are perfectly elastic. The meaning of perfectly elastic is that when they collide, they don't gum together, they rebound like electric, like balls. They rebound like balls. So they don't collide like plastic balls. They don't actually gum together. When they collide like that, they just rebound. Very, very important. So, and again, their cohesive force are negligible, and that's the reason why we said they can move. You know, People say there are forces. Some scientists said there are forces between them, but we say their cohesive force are negligible, and that's why you saw them. They are widely separated and negligible. Okay. Another kinetic theory they postulated was that the temperature, as temperature increase in temperature, increase in temperature increases the average kinetic energy of the particles. I've said that earlier in the class. Increase the average kinetic energy of the particles. And that's just few particles. So, and that's just few things about kinetic theory of gas. Yeah, some textbook is talking about five, but that's just the main kinetic theory of gas. So that is that for that. So very very important. Go over the class over and over again. Now let's now go to that question. Let's go to that question. Are we still together? Are we still together?
Yes, sir.
Okay. So let's go to that question now and see. Somebody will be answering the question for me to be sure you understand what I actually taught. So the question is, the droplet of water observed around a bottle of milk taken out of the refrigerator. Can you see that? Taken out of the refrigerator is due to the fact that the water vapor in the air around the bottle gains some kinetic energy, temperature of the milk drops as it loses heat into the surrounding. C. Saturated vapor pressure of the milk is equal to atmospheric pressure. D. Vapor pressure in the air around the bottle loses some of its energy to the bottle. Who is answering that question? Somebody? What's the correct answer? I'm waiting for somebody who is answering that question.
The water vapor in the air around the bottle loses some of its energy to the bottle.
Correct.
Yes.
Correct. Very correct. Okay, that's very correct. But let's see. Let's see why other options are not the answer, so that we'll be sure we understand the class. So let's analyze. A. Water vapor in the air around the bottle gains some kinetic energy. If water vapor in the air around the bottle gains some kinetic energy, definitely there cannot be condensation. I hope we are getting that. When you gain energy, what happens is that you vaporize. Is this explanation clear? When you gain more kinetic energy, what will be happening that you will be wanting to vaporize. You will not be wanting to condense back to liquid. So A cannot be the answer. B, temperature of the milk drops as it loses heat into the surrounding. The temperature cannot drop. The temperature will increase, because if you bring a bottle of milk from the refrigerator and you just put it on the floor, what will happen is that, let's say for example, maybe the temperature is around, let me even say it has not gotten to 0 degrees Celsius, or let me say it is even blocked already and it has gotten to 0 degrees Celsius. When you leave that bottle of milk, what happens is that it will be aiming to turn to liquid, Abby. And if it turns to liquid, it means that it is now acquiring temperature, is acquiring heat, is not losing heat, because the temperature will increase from 0 to around 27 degrees Celsius if you leave it. Do you understand that now? So the temperature of the milk drops. No, as it loses heat into the surrounding, it will not drop. So what happens is the temperature will increase, because it will increase from like 0 to 27. So B cannot be the answer. So let's go to C. Saturated vapor pressure of the milk is equal to the atmospheric pressure. If this happens, it means that the milk is boiling, because we have said that in our class that saturated vapor pressure, when it equals atmospheric pressure, it means that boiling has happened. So the correct answer is actually D. Very correct. There's water vapor in the air around the bottle. We lose its kinetic energy, and that's what causes condensation. When it loses the kinetic energy it has acquired before, it condenses back into liquid. That's correct. That is very very correct. So we can use all this knowledge to answer all other questions on kinetic theory. In the subsequent class, we are still going to talk about kinetic theory of gas. That will be second video. Okay. So do we have any question now? Question before we call it a day? In the absence of no question, so go over the lecture over and over again and try to answer some other questions on kinetic theory of matter. So thank you and God bless you. Or do we have question? Do we have question?
No, sir.
Are you sure you understand?
Yes, sir.
Question. No, are we sure? In the absence of no question, we meet again at the scheduled time in our other classes. Thank you. If you have any question, you can drop it on the Telegram group. If there is any, you saw any question on kinetic